everyone. Hi, Werner. Thank you for being here.
Hi.
Hello. I'm so happy to have you. Oh, hey, Jonah.
Hi, Nikki. Hi, Don. Nice to see
Hi.
you.
Thank you for being here.
Thanks for having me.
Okay. Let's see.
I will say, Jonah, you may not know, but be aware, but I did have this, the students did download some LIGO data a few weeks ago, just so they could look at HDF5 files and whatnot. So
Oh, this group, these students have
yeah,
tried
these
that?
very students, yes, indeed.
Wow, they're like experts. That's amazing.
Yeah, exactly. So no. Thanks to all that, all the open science data and if you want to plug the workshop.
Do, can, and will. Thank you
All
for that.
right.
Yeah, thank you for the note. Actually, if it's okay, I'm sure you have a full agenda, but is it possible that you could say just a word or two about who these students are and what they're doing? It seems like a pretty interesting group.
I mean, I could, or Nikki, if Nikki wants
No,
to.
go for it, Don.
Well, I mean, I don't want. So I'm going to generalize. So please, I want to invite the students to correct me if I say something wrong. But these are undergraduate students at U.S. institutions, and they are all interested. They are interested in. They have various majors: law, computer science, some in the sciences, some applied math or other math, and they are interested. And we've been what else about them? And we have a variety. They come from all 4 years. We have some freshmen, we have some sophomores, seniors, juniors. I think we have a fifth year senior too. They are interested in Some are interested in maybe pursuing like a more of a science thing. Some people are interested in more computer science or applications or software engineering. And we have a lot of people interested in astronomy this year or astrophysics things. Am I forgetting something? I can't, I don't know.
I think that sounds good. And students, as always, these are both friendly speakers. We didn't ask the ones that bite to come speak to you. So during the talk, please, ask them questions. I'm sure, will be happy to answer you. Yeah. So with that, I want to make sure we give you guys enough time. But before that, we want to make sure to mention that in your the shared drive, you'll be able to find more information about the group project. You'll have your group assignments are in there, as well as the list of major facilities and mid-scales that you can choose for your group project. And we ask that you guys get together via email, Discord, whatever your Zoom, whatever way works best for you guys, and choose your top three, two. I didn't see if that was three or two.
Three, three,
Three. Your top three
top three
choices,
choices.
and get those to us by next Tuesday. You can email CICF at ci-compass.org. So yeah, check those out, but not during these talks. So without further ado, I think Werner came first, so I'm going to let Werner go first if that works for you guys.
That
But
was my mistake.
so it's my pleasure
No,
to
that's right.
introduce Werner Sun from CHESS, and I'm going to let him take it from here. Thank you for being here, both of you.
Great. Thanks, Nikki. Thank you to everyone at CI Compass, Angela, Don, Nikki, for the invitation to speak. It's great to be here. Let me get my slides up. Give me a second. There we go. And I'm going to go to full screen. Do you see this in full screen?
Yep, that looks
Yes.
good.
Oh, okay, thanks. Yeah. So yeah, as Nikki said, feel free to interrupt me as I'm speaking, ask any questions, but I may not be able to see you because of the way Zoom is. And so, yeah, just feel free to interrupt. Um, my name is Werner Sun. I am the IT director for the Cornell High Energy Synchrotron Source, or CHESS, as well as its host lab, the Cornell Laboratory for Accelerated-Based Sciences and Education, called CLASS. So today I'll be giving you an overview of the cyber infrastructure we have here at CHESS. But first, intro to what CHESS is. So CHESS is a national X-ray user facility. It's one of only 5 high-energy synchrotron sources worldwide. And we are producing high-intensity X-ray beams that researchers come to us to study a whole wide range of materials, all the way from proteins and catalysts and plants, so organic matter to inorganic matter, like batteries and quantum materials, metals, processes like additive manufacturing, and we even can study paintings here. We have about 150 user groups visiting us every year, which amounts to over 1,300 external users. We've been operating since 1980, and we're supported by the NSF, AFRL, NIH, among other funding agencies. The X-rays are generated by the Cornell Electron Storage Ring, which is a particle accelerator that I'll show you on the next few slides. And we currently have 8 active beamlines or experimental stations, each of which is tailored to a specific technique. So this photo shows you the outline of the Cornell Electron Storage Ring, or CESAR, on the campus of Cornell University. And the CHESS beamlines are housed down in the bottom left, in that building at the bottom left, which is Wilson Lab. So the ring itself is about half a mile around in circumference. It's 40 feet underground, under the athletic fields. And it is circulating positrons, which are anti-electrons, the antimatter partner of the electron, at an energy of 6 giga-electron volts. And as the positrons are circulating this ring, they are emitting X-rays as a byproduct tangent to the ring itself. So all the way around the ring, X-rays are being emitted, and some of those are being collected and used at CHESS for scientific purposes. This is a view of the CESAR tunnel. You can see on both sides of the tunnel, there are electromagnets that are guiding the positrons in their orbit. And then looking at the CHESS facility itself, so this is in that building at the bottom left, in the picture before. This is the layout of the 8 active beamlines at CHESS, and you can see the curvature of the CESAR ring at the top. So as I mentioned, every beamline has its own specialty, and this just shows you the wide range of different disciplines that that CHESS scientists and CHESS researchers are dealing with. So this is a theme I'll be coming back to throughout my talk, but there's a big heterogeneity in our facility. There's a lot of different science domains, which means a lot of different types of hardware and X-ray techniques that we're dealing with, different data types, different analysis software, and different community practices. And all of this diversity is both a strength scientifically, but it's also a challenge when it comes to designing cyber infrastructure. To give you a sense of what these X-ray hutches look like, this is one particular hutch that works with functional materials, so 3D printing in particular. A hutch is basically a lead-lined room to keep the X-rays that shields, the X-rays, keeps them inside. And it's filled with lots of equipment. In this particular setup, the X-rays are coming into the hutch from the right-hand side. They hit a sample that's sitting in the circle in the middle, and then the X-rays that are scattered will be picked up, detected by an X-ray detector. That's over on the left. This is a close-up of what the sample looks like. This is just a placeholder sample, but this is about the size of the types of materials that that users will be bringing in to study. The detector that I just showed you is basically a CCD camera, But we have lots of other different kinds of detectors as well, spectrometers, fluorescence detectors. And so all of these are producing the raw data that's produced at CHESS. These data sets are multidimensional data sets because although they're composed of 2D images and 1D spectra, we're collecting these images and these spectra while scanning over a bunch of other parameters, like the position of the sample, or how we might rotate the sample and take data at the same time. We might subject the sample to different temperatures and pressures. So every time you add a parameter to study, that increases the size of your data set. We have many different kinds of detectors, so we have many different kinds of file formats, including HDF5, which I heard you just heard that you are playing with, Nexus, TIFF files, CBF files, and even just plain old text files. On the right, you can see a couple examples of the types of raw data that comes out of these detectors. And to make sense of this raw data, you need not just the raw data, but also auxiliary data such as calibrations and metadata that tells you what the sample is and how to analyze it in particular. The plot at the bottom shows you that the amount of data we've been collecting is growing over time. These days, some beamlines are collecting over 200 terabytes per year. And in some cases, the larger data sets might be 10 or 100 terabytes collected over the course of a single week. So in addition to raw data, so starting with the raw data, the raw data sometimes, for particularly large data sets, might be reduced on site at CHESS with some preliminary processing where calibrations are applied and the bits are converted to physical quantities. This reduction process can be manual or automated, and it's usually performed by CHESS staff as a service provided by the facility. And this reduced data set is often a little bit smaller than the raw data and easier to work with for the users. And it comes with its own set of metadata. So then at this point, the user will take either the raw data or reduced data set and analyze it for themselves using their own domain-specific software. It may be software they've written or purchased from a third party, and they might be doing this either on-site at CHESS or off-site at their home institution. And analyzed data, of course, comes with its own metadata as well. In terms of data products produced by CHESS, we also have other research artifacts, such as the code that's being used both to collect the data and to analyze the data, as well as AI ML models or data visualizations. Basically, anything that's used for decision-making as you're doing an experiment should be considered a research artifact that should be preserved and made available. So on the right over here, you can see some examples of both reduced data and analyzed data. So for a number of years, we've been supporting this sort of data collection, data analysis workflow using what I call the CHESS CI 1.0, which is infrastructure that we've deployed based on decades of experience that we've had here at the lab doing high energy physics experiments. So for data storage and archival, we have the so-called CHESS stack system, which is about 2 petabytes of disk arrays that are connected directly to the X-ray detectors over a private network. This raw data is backed up nightly and archived to magnetic tape 3 times a year. And we, in general, keep the raw data on disk for 6 to 9 months. And if it's no longer on disk, it can be restored from tape upon request. To analyze this data, we also provide a compute farm, which allows users to process large data sets without having to transfer it back to their home institution. There are about 50 nodes in the compute farm right now running Linux, and they all have direct access to the CHESS stack file system. In total, there's about 1,300 cores and about 8 terabytes of RAMs. We also have a queuing system that supports interactive, batch, parallel, and GPU jobs. For remote access, we use a combination of no machine and Globus and SSH. So users outside, when they're offsite, can remote in. So from a user point of view, there are many different ways a user can be interacting with this cyber infrastructure, this CI 1.0. If you have a small data set, all you're really going to be doing typically is downloading the data from the CHESS stack after it's been collected at the beamlines. And then you'll be doing your data analysis either on your laptop or your home institution, and then publishing it from there. But more and more, we're seeing larger and larger data sets of chess, and so that involves much more use of the cyber infrastructure we have here. You might end up with a data set that is just too large to transfer to your home institution, in which case you'll need to use the compute farm here and the software that's installed there to do your data analysis. And as I mentioned before, there might even be a data reduction step in between that also uses the compute farm and is performed by facility staff. So this ever-increasing data volume means that we need to layer more infrastructure on top of the CI 1.0 in order to fill the gaps, in order to provide scalable solutions for monitoring, for processing, for fair data, for code development and user interfaces, and of course, these days for AI readiness as well. So we are currently developing CHESS CI 2.0, which is a layer of components on top of the 1.0 infrastructure to fill these gaps with different capabilities, different pieces that do data visualization. We have a science gateway to help with code organization, fair data services, and cyber training. And this is what I'm going to talk about for the rest of the talk. So for data visualization, we are partnering with the National Science Data Fabric, which is a NSF project to democratize access to large-scale scientific data by connecting sites all across the country, data sources and compute resource, connecting them together with high-speed networking and a software stack. Together with NSDF, we are developing these web dashboards to help visualize chess data in real time. It's based on this Open Vistas package out of the University of Utah. And the idea is to provide data quality feedback for chess users while they're still on site so they can collect any errors that might crop up during data collection. It also allows them to identify, see something interesting in the data and sort of pursue that while they're still here. And it facilitates remote participation by researchers offsite. So we currently have these NSDF dashboards deployed at 3 beamlines at CHESS, 3 very different beamlines that are all doing different techniques, have different directory structures and file formats in their data. And the dashboards are able to handle this heterogeneity. You can see an example of a dashboard down here in this black box. This is basically visualizing a stack of 2D images. So think of it as a 3D volume that you can look at slices of on the left. And then you can pick points to make projections through this 3D volume, like this red curve here, which is a 1D projection of the 3D volume along this red point pointing into the screen. These dashboards are available over the web, and that got a great use on the very first experiment that we deployed the dashboards with. You can see a picture of the people involved on the right here. So we had the NSDF team here on site as working with CHESS as well as a user group from the University of Michigan. And it just so happened that the PI for this user group wasn't able to make it out to CHESS for this beam time, but because of the dashboards that we had just deployed, they were able to follow along the experiment and participate in decision making by pulling up the dashboard at their home institution. We're also collaborating with the NSDF. I'm not going to talk about this much, but a new collaboration for cross-facility AI capabilities together with NSDF and Oak Ridge National Lab. And the idea is to engineer a self-driving X-ray diffraction experiment at CHESS, but using compute infrastructure at ORNL. So we hope to be doing this later this spring. So that was visualization. Another user-facing tool that we've built is a science gateway. So we have an instance of the Galaxy Science Gateway tailored to materials science that we call X-Image, or X-ray imaging of microstructures gateway. And what Galaxy does for you is it turns very complicated spaghetti workflows like the one you see on the top right here, and recast them into an intuitive graphical form that's also modular that you see at the bottom. So this nice UI hides the details of the underlying cyber infrastructure, and it also records the history of the analysis that you're performing. So it gives you a provenance that you can retrace your steps afterwards, and also hand off complete workflow to someone else if you need to. What we discovered in building this Galaxy Science Gateway is that just a Science Gateway is not enough, that we really needed to reorganize the underlying code and add data management capabilities. So another thing that we've introduced is the chess analysis pipeline here, which is an object-oriented model for refactoring monolithic Python programs into pipelines that are composed of interchangeable, reusable code components. So if you think about a data processing pipeline, what you're doing is you're reading data in, you're doing something to that data, and then you're writing something out. So those are the base classes within CHAP. It's a reader, a processor, and writer that you can link together to build pipelines of varying complexity. The reader and the writer here will handle all the chess-specific logistics. And so the subclasses, we have subclasses for different data formats. And then in the middle is the algorithm itself. And the algorithm is meant to be independent of chess. So users from outside of chess can develop their own algorithms and plug them into this pipeline. At the moment, we are in the process of quote unquote chapifying our workflows. And down here, you can see a diagram of how you can use this framework to build more complicated pipelines. For example, and this example is a sketch of how you might use CHAP to do a self-driving autonomous experiment. Taking a step back and looking at the bigger picture, we are at the moment focusing on building infrastructure for automation and AI readiness. And both of these things require data sets to be described by rich metadata. But what we find is that in practice, metadata right now is often recorded in non-standard ways. They can be notes written down on paper. You might be encoding metadata in your file names themselves. And so the thing is, if you had, and doing it differently every time doesn't allow for automation. So if you had machine readable metadata that is consistently recorded, that would increase the efficiency and reliability of all your downstream processes. Metadata would be easily retrievable by data processing jobs, which also gives you, with a minimum of human error, minimum of human input, which improves reproducibility and allows you to comply with the FAIR guidelines. You can also use the metadata in AI workflows, both for finding training data sets, but also including it directly in model training or in a RAG context window. And so metadata can actually help increase the trust in AI by letting you, by validating the provenance of your training data sets and reducing the bias in the outcomes. So our goal is to build tools to record metadata and other research artifacts in real time. And one of the design challenges in doing this is the heterogeneity that I mentioned before. And we also, the metadata that we have is also a mixture of structured and unstructured. It can be high volume or low volume. And so what we've developed is the we're calling it the Fair Open Science Extensible Data Exchange Network, or FOXDEN. And FOXDEN is a suite of data services that are basically web applications with backend databases and command line APIs that allow you to do this real-time metadata recording. FOXDEN is not a data acquisition system. It's not a storage system or a workflow system, but instead it's a management layer that that works with these existing systems. And the strategy here is to decouple the metadata, which is small and portable, from the data files themselves, which can be large and hard to transport. So the other thing that FOXDEN has is a DOI publication service. And the idea here is that the metadata that you're collecting in real time in FOXDEN is already publication ready. And so with this publication service, you can publish that metadata mint a DOI with a single click without doing any further preparation. And this lowers the barriers for researchers to do data publishing as soon as possible. And the way that FOXDEN deals with the heterogeneity that I mentioned before is that we're using a service-oriented architecture, so it's not a monolithic system. Different services can act independently, and they can be composed to support different usage patterns. And you can invoke FOXDEN services from a wide range of software over HTTP and JSON files. And Beamline scientists and users can define their own schemas for every application that they have. So this diagram shows you a typical research workflow that we have at CHESS that goes from data collection all the way to data publication. And you can see that at every step along the way, you can invoke the FOXDEN services to record metadata records that are linked together through provenance records that identify the parent and child of every data set. And at the end of the process, when you're ready to publish, you can use the publication service that I mentioned earlier to mint a DOI for this entire chain of metadata and make it available publicly. So the status of FOXDEN right now is that it's currently operating at half of the CHESS beamlines. We also have a cross-facility collaboration where we're deploying FOXDEN at MagLab, integrating it with operations there. And we are also working on a RAG-based chatbot as part of FOXDEN to provide more analytic capabilities with the metadata. And we're also looking into a governance structure for security and accountability. So I just wanted to show you a couple screenshots of FOXDEN. On the left here is search results for metadata. And if you click on a particular record, then you can view the record itself in a number of different formats. And when you're ready to publish this record, you can click the Create DOI button, and that takes you to another screen, which mints a DOI. In this case, it's on Materials Commons. So this is a CHESS metadata record collected by FOXDEN that is now in draft form on Materials Commons. The idea with the publication is this is lightweight publication. We're only publishing the metadata and provenance records. We are not uploading the data itself to Materials Commons. The data, because it's so large, remains at CHESS, but we are including instructions for data access in the DOI. And I've shown you here how it works in Materials Commons, but you can publish also with DataCite and Zenodo, and it supports both draft and public DOIs. And this makes CHESS data, data sets collected at CHESS available down the road for AI model training by other parties. So it's a form of data reuse that we're enabling here. Since I'm running out of time, I'll just flash a model of the AI chatbot that we're using or developing that uses retrieval augmented generation, and I'm happy to talk about this afterwards if anyone's interested. And this is I'll also skip this, but this is a future vision for FOXDEN where we are deploying a Foxton federation across multiple facilities with shared storage resources. So the last thing I wanted to mention, the last piece of new cyber infrastructure that we're working on is a cyber training program that is a partnership with our friends here at CI Campus that is meant to reduce the barriers to the use of CHESS CI and NSFSI CI by CHESS users. And the idea here is to accelerate the progress of X-ray science for a broad user community. So we are developing a CI training program that addresses basic computer and data science knowledge and skills, and also teaches best practices for data collection, data curation, and dissemination. So we have training modules on Linux and Python and distributed computing, X-ray science software, so this is domain-specific software, as well as how to do data curation and fair data. We have videos posted on YouTube and a website that you can go check out afterwards. And we hold yearly workshops in person at CHESS, and we do tutorials at domain conferences. So this is a training program that is meant to go along with the other cyber infrastructure that we've developed to help prepare CHESS users to make the best use of both their beam time at CHESS and also the CI that they need to analyze their data. So that's basically it. So in summary, CHESS cyber infrastructure is evolving to meet new challenges and opportunities. In going from version 1.0 to 2.0, we're focusing on automation and AI readiness, using a multi-pronged approach, developing a wide range of different components with lots of external partners. And I will end by plugging our CICF summer projects. We're offering 2 summer projects with scientific applications of AI and ML, and both with image classification applications and parameter optimization. And the types of topics that you'd be exposed to in these projects are Python data analysis, machine learning techniques, data curation. You'll get to work with Foxton and retrieval augmented generation. And again, I'd be happy to talk about this or anything else in my that I covered afterwards. So thank you.
We do have one question in the chat, although I do want to make sure that we give Jonah all his 30 minutes. So maybe, Jonah, do you want to start pulling up your slide and Werner, you can answer this quickly maybe, or?
Sure. Very basic question. Why do you need such a large accelerator for X-ray? Yeah, let me answer the first one quickly. So the X-rays that we're producing are actually, you're right, they're very similar to the medical X-rays that you would get in a doctor's office, but they are incredibly high intensity. So think of the difference between a flashlight and a laser beam. We are producing, the equivalent of laser beams with X-rays, that sort of intensity. And that is why you need, you can't just have a lab source, you need an accelerator to do that. For the chatbot for RAG, I can share some more information, but this is very much under development, and it's something that we're experimenting with, but it's also something lots of other people are experimenting with, and I can throw some references and make them available afterwards.
Awesome, thank you. Jonah, whenever you're ready.
Great. Let's see what we can do here. All right.
Looks good.
All right. Great. Nice to see you. Hello, students. Thank you for spending a few minutes with me today. My name is Jonah Kanner. I work at LIGO Laboratory. LIGO is spread across a few different sites. I work at Caltech, which is a small university in Pasadena, California, outside of Los Angeles. To briefly introduce, so this talk is really a data talk. I think that's what this is about. So the science here, I've kept it to one slide, and then we've got a lot of notes about data. If you want to talk about black holes, that's a whole other talk that I'm happy to do another time. Sorry. But what we've got here on the first slide is we've got just some images of the LIGO project. So LIGO is a interferometer observatory. We are observing gravitational wave signals from merging black holes in outer space. So what's happening in the images is on the left side, we've got this. This is actually an image from a computer simulation of two merging black holes. So black holes, like stars, well, black holes are the remnants of dead stars, and many stars exist in binaries, and so they orbit each other. And as black holes get close enough in their orbits, they start emitting gravitational wave radiation. As they emit radiation, they get closer in their orbits, they speed up and they emit more radiation. So it's a runaway process. And at the moment when two black holes merge, there is this burst of gravitational waves, which we're able to read out in our detectors. So these are photos of our two. Are you able to see my red cursor? Is that possible? So these are photos of our two observatories. There's one in Washington State in the desert, and there's one in Louisiana in the forest. And when one of these gravitational waves from merging black holes comes to Earth, um, in Einstein's gravity, gravity is synonymous with the metric of space-time. So what that means in practice for us is when a gravitational wave passes through, we have these very long, 4-kilometer long tracks, which we measure. This is humanity's best ruler. And the length of these 4-kilometer tracks is measured precisely using lasers. And when the gravitational wave passes through, the tracks shrink and stretch, and then we're able to read that out as a signal. So on the right here, we've got some example data. This is a characteristic chirp. So this is in time on the x-axis and frequency on the y-axis. And so you read this out as boop, which is the sound of two black holes merging. So that's what we do. We're finding these gravitational wave signals that come from outer space, and we're recording them in this time series data. Okay, so for me, when I think about data access, and in particular fair data access, I'm really interested in the challenge of a person encountering our data for the first time. Sounds like you all had that experience a few days ago. I'd love to hear how that went. And I think about this as like a problem in transportation that's known as the last mile problem. So in transportation, you might have these networks of public transportation. So you might think of like a train network. Here in Los Angeles, we have the metro. This is the New York City subway map, which is a very dense network of train lines that run all throughout the city. And, once you're on a train, it's relatively simple to, travel to other stations and switch to other trains and get where you need to go. But there's this classic problem called the last mile problem, which is that very few people actually live at a train station. Instead, most people live some distance away from a train station, maybe about a mile away. Actually, in my case, that's true. My son needs to get literally 1 mile to the train station every morning in order to get himself to school. And so this last mile problem is how do you get a person from home to the train station? So in data access, what am I talking about? Why am I talking about trains? Because I'm obsessed with trains. That's why. But the other reason is because these train networks, I think of analogous to our expert networks within our academic communities. So um, we have these academic communities where the traditional way to gain access is to go to somebody's office, sit in their office as a graduate student for 6 years, learn from them directly, repeatedly encounter problems, ask questions, and get answers immediately. And then that's what gets you access to this network. And once you're in the network, now you have colleagues, you have papers you can read, you have very complicated documentation that's difficult to parse. Maybe you can just look at the code and understand it. So once you're one of the experts, there's quite a lot of resources available. But coming in as a new student, as someone from a new field, uh, how do you gain access to that expert knowledge? Okay, here's how my son gets to the train station. He uses a bike, so that's my physical solution for the last mile problem. But for data, what are we doing? Well, we have, any number of people coming in who might be high school students, undergraduate students, yourselves, new graduate students, experts in other fields. Amateur scientist is such an interesting category. We hear from these folks all the time. Hi, my name's Jim. I'm a retired engineer and I'm really interested in, I saw, I read a book about LIGO and I'm really interested, and I'd like to get started. Sometimes even artists who want to like make music or art with our data. Great. And so we have this sort of gap in access and knowledge and resources. And for me, my kind of obsession is how do we close that gap? How do we take somebody who's never seen our data before, never worked with it, doesn't know anything about it, and get them to a place where they can access all the expert level tools, the data, the software, the journal articles, the conferences, the colleagues. How do we get that process started? And more or less, that's what this talk is about. Sorry, I'll try to be mindful. Oh, I don't have a clock. Someone's gonna have to yell at me about time. So having said that, I think about this diversity of data users as kind of a terrible word for people. So I think there's a diversity of people. And I don't know if this is true, but it's my belief that there's a lot more non-experts than experts. And so I imagine a pyramid of knowledge levels, expertise. And I imagine that there's a lot more people who are interested in our data just a little bit than people who are experts and interested in a lot. And these sort of different types of folks have sort of different needs in terms of what they need to access the data well. For non-experts, I think that maybe they want lots of services. So what I mean by services is like software services, so a web page that they can go to, a web app that they can connect to and use right away. Can they browse the data without having to write computer code to see it? Non-experts might need lots of support. Which means they might have questions, and how do we answer their questions? They might want to use like web pages to access data as opposed to an API. And for non-experts, too much detail might be confusing. And that's sort of in contrast to a more expert user who, instead of lots of services, might want access to lots of different types of data, might have high demands on computing resources, on data access, on APIs for, so that they can do things by scripting. And for these expert users, a lot of times the details will really matter. So you have to have documentation that really gets into the weeds. And so somehow, and both of these sort of groups of people are very important. The experts, of course, are very important because they're writing papers and grants and their careers depend on it. And the non-experts are also very important. Um, because that's where we get new students from, because it's a lot of people, because ultimately we're serving the public in what we're trying to do. All right. So, and these are the types of questions that come up in practice that might create challenges for data access. Sure, we can make our data public, but, are they easy to find? Do I recognize the file format? Can I figure out how to open it? I don't know if, actually, I'm curious if the students have found yourselves in this kind of situation where you're working on a new project and you're given a file format that you've never seen before. Here it's data.wtf.gz. And so what do you do with that? I feel like I spent the first like 2 years as a graduate student trying to repeatedly answer that question for different file formats. Um, this this next bullet is one that I thought is so interesting because I would have never dreamed it. So coming through graduate school and the people that I'd met, it never occurred to me to want to load LIGO data into a spreadsheet. But the minute we set up the Open Science Center, that's one of the first questions we got is we get here from like amateur scientists or high school students. And the point is, they're not using our tools. We have some set of tools that experts have developed and used and share with each other, and we think are great, and it's like a mountain of Python code. But then here comes retired engineer Jim, and he said, "Oh yeah, well I really want to load your data into an Excel file. How do I do that?" And we were absolutely stumped by that question because it had never in a million years occurred to us that that's something someone wants to do. But the reality is that a spreadsheet or a text file is incredibly basic. You can use it with, 100 different types of software tools, most of which I would have never even thought of. And so it makes sense to give people access to data in a way that's uh, easily accessible and flexible. And this goes on and on. So there's all kinds of challenges that a new person or student might encounter. And so, here's how that's kind of played out. These are some examples of how this sort of played out for us. We were using a special file format. We called them GWF files, which no one has ever heard of. It stands for gravitational wave frames. What's a GWF file? How do I open it? Real humans don't know the answer to this question. So that was a challenge. Data access requires programming. We think of experts as, programming's easy. Everyone knows how to program, but a lot of people don't. So what tools do we provide people if they don't want to program? Um, we had a lot of, we still have, but had a lot of specialized libraries without examples or documentation. So even if I can give you the whole software stack, can you install it? Can you run it? Do you know what to do with it? And people need, they need help. They need examples again, examples that a human can use, not not a cryptic documentation that maps out the keyword structure or something. Um, yeah, and then people need a little bit of signal processing, so we had to find a way to introduce people to signal processing who weren't familiar with it. And also our data are very messy. They contain all kinds of noise artifacts. And so we had to find ways to share that with people and help them understand sort of all the warts on our data. And here's some of the solutions to those sorts of problems. We now make our data available in multiple formats, including both GWF and HDF. So HDF5 is like a more popular format. We now support both. We also have a streaming data available, which is read directly into memory, and you don't even have to care about the file format. And then it's not listed here, but we actually do also make the data available in text and CSV files. So if you want it that way, you can get it. Um, we have a lot of software examples. A lot of these live in Jupyter notebooks, which are nice because you can look at them in a web browser without having to run anything. So you can see the code and the output right away. Um, we've put a lot of work into online tools, and I found that those are really important because if the first, software installation is a barrier because everybody's computer is different and not everybody knows how their computer works. And a given software, particularly like academic software that's written by grad students, might not run on everybody's computer. So we found that it's really important to have tools that run in the web browser without installing software. So here we're thinking about things like Google Colab or MyBinder to run Jupyter notebooks. Um, and then Streamlit is one example of a whole class of online dashboards or online web apps. And Streamlit just happens to be the library that I've picked up on and tend to use. But just in general, my message is if you run things in the browser instead of expecting the user to run them on their computer, it just totally removes what I think is a huge barrier to entry. And then we also have a help desk and a discussion forum so people can ask questions. We have workshops and online courses. And then we try to make everything available through one point of entry, which is gwasc.org. So it's terrible to say, GWASC. My wife says it sounds like a frog, but it's Gravitational Wave Open Science Center. So there it is. It's all there. All right. I'm sorry I have to ask, but how am I doing on time? I don't have a clock in front of me.
It's at 9:48 right now.
Oh,
You have until
okay.
the end of the hour.
Okay, fantastic. So yeah, I'll show just a few examples of that. So software examples in the browser. Um, in this particular solution is Jupyter Notebooks, and there's a number of services that will run Jupyter Notebooks in the browser. Google Colab seems to work pretty well. We've used MyBinder in the past. We do, for what we're trying to do with these Jupyter notebooks, there are a bunch of specialized libraries, mainly in Python, because that's what scientists seem to like these days. So there are a number of libraries that are built and specialized for gravitational wave data analysis. And so what we wanted was to give people examples of using these libraries that do basic tasks that they could run in the browser without having to install anything. And so right away, you see the code, you can run the code, you can edit the code, and you see how the output changes. And hopefully that bootstraps the process of getting people started with the specialized software. And that's on our tutorials website, a tutorials page on the guasc.org website. I've gotten really into so then, again, trying to remove the need to program things, web apps, GUIs. What's something where someone who doesn't know anything can come in and right away have an experience, have an interaction with the data. The other thing, I put this note, but I'm sorry that this keeps coming up, but I have this note here about the CSV or text files. Again, we don't store our data in CSV files. That would be incredibly inefficient. Um, we would need like an extra petabyte of hard drive space or something because CSV isn't compressed. So instead, what we've done is we've made these web apps that on the web app will let the person choose which data they want. So you can come over here, you can choose which event you're interested in. So this person is going to pick 150914, which is one of our gravitational wave events. The web app is going to query our web server. It's going to use our API. It's going to download that data at runtime, produce these plots. And so now the user is able to make customizable interactive plots right away. There's links here that if the person wants to download the data in like a CSV file, they can do it. Um, and so that instead, so this is a case where instead of repackaging the data ourselves and having to manage a second copy of our data archive to support different file formats, we've made a web app where people can create on the fly the file format that they want. Um, I, let's see, this is that same web app running again. So that's nice. And then, we do manage a few different data product types, but the gold is sort of our strain data, which is the main time series output from our interferometer. And then because we're always thinking about this range of users, we have one primary data archive, but then we make it available through multiple access points. So there's something called OSDF, which is great if you're running on computer clusters. So this is sort of a service that we don't manage, that someone else manages, that we're able to take advantage of. There's this network data server, which is an in-house thing, but it provides streaming data for folks who want it that way. And then the web access, which is basically point and click on a web page. So this web access is intended as the lowest barrier for entry, where you can sort of point and click and download one data file at a time. It does also have an API, so it is scriptable. But then there are these sort of other tools if you want to scale it up to larger computing resources. And this is sort of an example to show what it looks like to download some data. It sounds like you've all already done that, which is amazing. And this is all just to show it's a point and click interface on the website. So you can go to guas.org, and then in about 4 clicks, you're at this page where you can click the file format you want, and it'll download the data straight to your computer. I like to think it's easy to use. I don't know. If you found it was hard to use, I'd love to hear that. And then finally, I'll have this note about supporting the community. So we do try to make ourselves available. So we have a discussion forum, we have a help desk, we have an online course, which is actually an annual open data workshop, which is coming up. So we can kind of plug that. There are these web apps and then also tutorials. Everything's available through guas.org. These open data workshops, we've sort of scaled them up. So we've gone to a hybrid format that involves about 1,000 participants each year at multiple locations. So we call these study hubs. So we invite people to set up study hubs and participate. It's very easy to set up a study hub because we provide all of the materials. So you don't even necessarily need an expert. So if you wanted your own study hub with your, you know, at your university or with this CI Compass group, great, that could be done. The next workshop is coming up April 20th through 23rd. There's a link there where you can find all the materials and register if you're so interested. But these are free hybrid workshops. So all the materials are online. There's actually an online course. We pay for a online course software called Thinkific that you can use on your own if you want to. It's all available. But then we also encourage these study hubs, which seem to be a really great model. And just to kind of show what this looks like, this has been really global. So this is a small one at my university. Here's one in Mexico. So this, I think these photos are actually from a few years ago, but you can see a few different cities here in New York, in Paris, in Illinois, in France, in Korea, in India, in Italy. So it seems like we're able to get about 10 to 15 of these study hubs each year. And so it makes for a pretty broad audience that's participating um, in the workshops. Okay, I've talked a lot. I'm just gonna stop. Maybe I'll just brag a little bit that we're at, not so long ago, we crossed the 1,000 citation mark. So there are now over, at this point, actually, as of yesterday, it's 1,100 scientific papers that are citing our data. So we think that this effort to make our data broadly accessible is having a pretty significant impact on the scientific and educational communities. And I will stop. Thank you all so much. You endured a lot of information, and I'm happy to take questions.
Oh, we already have one in the chat.
Yes. I just want to say that when we downloaded the data, we used wget, so they did not browse the interface. So
Great. Yeah, I love that. So there is an API. Maybe you found that, or maybe you just put a URL into wget. All those things are possible. So it's intended to be, um, the intent is that folks can access it using whatever tools they want to bring to it, and wget works just fine. Okay, so I'm supposed to read the chat. How does LIGO differentiate between gravitational wave signals from binary black hole mergers versus neutron star mergers in straining data? Oh my gosh, I'm so glad you asked. So that's a process called parameter estimation. And so general relativity predicts the waveform associated with sources, and it's a very strong function of the mass of the source. So basically, we fit the data. Actually, I'm so glad you asked because I have a web app for this, and I was looking for an excuse to show it off. So there's a rule that live demos never work, so I assume this won't work, but I'm going to try it anyway. So this is one of our web apps. And what you can do, you can select your event here, and then at real time, it'll download the data and then make a bunch of plots. And I guess for your particular question, I'll show you this waveform fitting feature. So the data here are in gray. Actually, this is pre-processed data. But it's time series pre-processed. It's whitened and filtered data in gray, and that's a time trace of the gravitational wave signal. So every time the data go up and down, the binary is going through one orbit. So you're literally tracing the motion of the compact object. And then the orange trace is a model, a theoretical curve that falls out directly from Einstein's theory of gravity. So from general relativity, you get these orange curves, which are theoretical waveforms. And then it's really the frequency evolution. So the space between the peaks of the orange curve corresponds to the mass of the system. And neutron stars have lower masses, around 2 solar masses. The black holes we're seeing are bigger. They're like somewhere between 10 solar masses and 100 solar masses. And so by fitting these theoretical curves to our data, we're able to infer the mass and so the source type, along with a bunch of other parameters as well.
Great. Any other questions for our speakers? And I think for both speakers, since we didn't have time for Werner earlier.
So can you all tell me, like, what is it like for you? Like, what was it like to download LIGO data? Did do students who are confused about new data, is that resonate for you, or are we past that? Is it easy now? Do you just ask ChatGPT and it tells you what to do? Or is there still like this experience of I don't know how this works? Or are you guys all super smart and you don't need tutorials because you can just look at it and figure it out? What is that like for you?
Don't be shy, guys.
They are shy.
I know.
What are you guys like undergrads or something? You just sit
Yeah.
in the back of lecture and fall asleep? Is that how school works these days? All right. So Leo wants to know, are LIGO data constantly recorded or are pre-processing necessary? I feel like the data would be massive. Both. We do record all of our data. I guess by pre-processing, you mean, yeah, do we pre-process it before we record it? Not much. Our data by modern computing standards, our data rates are not so high. So LIGO detectors are actually compared to like a radio instrument or other astronomy instrument, LIGO data sampling rates are actually pretty low. So we sample at 16 kilohertz, which is we take 16,000 data points per second. And so if you add that up over a year, you get like for in our main data channel, it's like a terabyte per year. So we can record all of that. We do also have auxiliary channels to monitor the state of the instrument, and that's a much, there's 200,000 of those channels, and there we do get to more like petabytes per year, which is a bigger scale. Um, but no, we pretty much keep all of it, actually. Most of the time, fetching the data, I feel like it isn't necessarily confusing since a lot of resources are accessible. That's amazing. It's the processing. Oh, that's cool. It's the processing and cleaning part that gets confusing. Absolutely. I love that comment, right? Because it's like, yeah, I can find the data, sure, but what do I do with it? And yeah, I think of these, the pre-processing and data cleaning. I mean, I think of those as secret steps, right? Because it's like something that like every graduate student's going to do. But when you're coming in for the first time, you don't know about it. I ran into this with astronomy. The first time I encountered an optical telescope, I thought, how hard is this? It takes a picture. But no, you need flats and darks, and you got to calibrate and, whatever. There's all these calibration steps that you don't know about. Yeah, Gemini and AI is a big help. That's true. I love that. Um, yeah. All right, Nikki, I don't know. We're over time. Do you want to stop? Do you want to keep going? What are we doing?
Yeah, I was just gonna say to the students that if you need to hop off, you can. But Werner and Jonah, well, first of all, thank you both so much for being here. But we have 15 minutes of office hours if you want to stay. And I don't know if any students want to stay and ask some questions. We'd be happy to have you.
Yeah, I'm happy to hang around. But thanks,
Great,
everyone.
thank
This was
you.
great. A lot of fun.
Thank you.
Yeah, thank you very much. There is a question in the chat, actually.
Yeah, there's a question in the chat.
Name.
Talking
I'll
about
just read.
academic.
I'll
Yeah.
yeah read it out loud. For large, unique facilities like those at CHESS and LIGO, are the backend and user and scientific or management software primarily developed and maintained in-house by graduate students and research staff, or do you rely on third-party software vendors? Given how specialized each facility is, how do you handle long-term maintenance and scalability?
Man, that's a great question.
That is a great question.
Yeah, you guys aren't undergrads, are you? You're like some kind of super students, aren't you? Um, yeah, so this is a great issue. I can say for LIGO, it's both. We do like to use off-the-shelf software when we can. In general, if we use something off the shelf, it usually saves us money in the long run because it's easier to maintain. And we have an awful lot of in-house stuff. So we do have LIGO Laboratory as a project employs about 150 people. not all of those people are working on software, but some of them are. And so we do have, in-house people, including myself, who have a full-time job to sort of keep all these things running. And so, yeah, we do have some in-house software that we rely on, and we pay the cost. We pay humans to maintain it. Um, how do we handle long-term maintenance and scalability? Yeah, I mean,
Mm.
it's hard, but the short answer is that we keep staff, and there is a pretty significant maintenance burden, that it is a constant struggle, to be honest. I mean, there is always a tension. We always feel like we're short-staffed. So we do have kind of a constant tension between wanting to maintain well the software we have and also wanting to develop and try new things. Um, and so that, that ultimately becomes a management issue. Yeah, I don't know. Werner, what do you think?
Yeah, yeah, and just to follow on that, as someone who is in management, that's part of the calculation is the long-term maintenance. You have to consider the technical debt that you're incurring whenever you embark on a new project. And so not only how much resource do I have, right now, but how much am I going to need in the future, 5 years down the line, to keep this software going? Um, and sometimes that's unknown, and so you just have to make your best guess. Um, the the rest of it, for chess, it's very similar to what Jonah was saying. Like I said before, at chess we have a wide range of disciplines, and so the software, the kinds of software that we're using depends on the discipline. So structural biology, for example, is very mature, software-wise. They've been doing computational biology for years and years, decades. And so there are lots of open source and third-party software packages out there that are just commonly used in the community, and that's what users expect to use when they come here. Other disciplines like material science are relatively new to computational science, and so they are building it as they go. So they have developed their own software packages. Some of the larger packages have been developed by former chess users, and we are leveraging that for all of our other users. But I would say that those packages they're changing all the time. There's a lot of ongoing development, um, and it is the sort of thing where grad students are involved, postdocs are involved, facility scientists are involved. So there's a real mix of different kinds of software and different ways that you have to approach, software development and maintenance because of that. Did I answer the question?
Yeah, thank you.
Yeah. Mhm.
Dia has a question for Jonah in the chat.
Right. Yeah, so getting started, I mean, with LIGO specifically, so we do have these open data workshops. There's one coming up April 20th. I definitely, if you want to start to dig into our tools a little bit, that's a great opportunity to get started. And that's free, it's online. Or if you're really ambitious, you can try to either find a study hub or start a study hub and work in person with a few other students. So I definitely recommend that if you're interested. We do, it sort of depends what you want to do. Usually, the conventional wisdom is that the path into this field is through graduate school. So a lot of our staff have PhDs, and at some point they, went to graduate school and worked on the project there. That was the advice that I got many years ago, and I followed it, and at least in my case, it worked out. Having said that, we also do hire staff without PhDs. So Caltech does have a jobs posting website, and we usually have a few jobs posted either for, mechanical engineers, software engineers, operators. So we do have, so if you want a job, you can look at the kinds of jobs that are there. That's a place to look. And we do also for undergrads, we do run undergraduate summer research. So we have what's either called a SURF program, Summer Undergraduate Research Fellowship, or an REU program, Research Experience for Undergrads. We tend to call it the SURF program. So if you Google for LIGO SURF, that is a program that you can apply for. It is a little competitive. We're going through applications now for this summer, but that is, that is available for undergrads. Um, and then, we do sit in a large scientific collaboration. So there's something like 1,500 or maybe 2,000 people in the LIGO Virgo Cagra scientific collaboration, which means whatever university you're at, there's some chance that there's somebody there working in gravitational waves. Go talk to that person, right? If you're at, I don't know what schools you're at, but if you're at a major research school, odds are there's somebody there working in gravitational waves. And go talk to them and see if you can get like a summer research project or whatever. So there's a lot of opportunities there to get involved. Hope that helps. Oh gosh. Okay. What, when the pipes detect gravitational waves, does it actually visibly shrink? Or is that shrink in the pipes only detected by some other machine and is not visible? Yeah, so the length changes we're talking about are very small, and by very small, I mean foolishly small. So we're talking about 1 part in 10 to the 22 over a track that's 4 kilometers long. So we're talking about a length change of like 1 times 10 to the minus 19 meters, which we like to point out is considerably smaller than the radius of a proton. So we're talking about microscopic changes, but not even microscopic changes. We're talking about like sub microscopic changes. This is the world's most precise length measurement. So do you see it with your eyeball? No, you do not. How does it work? We use lasers. So the tracks are 4 kilometers and we bounce a laser beam back in. There are mirrors at each end and we bounce a laser beam back and forth between those mirrors. But then it actually forms an L. So there's 2 tracks. So there's an L. There's a 4 kilometer tube this way and a 4 kilometer tube this way. So maybe say east, west, and north, south. And then the shrinking, it turns out it's a shrinking and stretching that goes in this kind of pattern. And we use interference in the laser light to read out a difference in length between the 2 tubes, and we do that very precisely. I was wondering what information does the data provide or help with in regards to uncovering new properties of black holes and physics at that scale? Gravity and quantum theory, perhaps. Yeah, so yes, that's the fun of it. Um, so there's a really there so these signals turn out to be one of the best ways to test the theory of general relativity, which is Einstein's theory of gravity, in the strong field limit. So, gravity of course works really well like in our solar system. Planets go around the sun in exactly the way we think they should, but that's relatively weak gravity. Black holes are special because the gravitational field around them is very strong. And you can imagine maybe Einstein's theory works fine when gravity is weak, but then when it's really strong, that's when you start to see things look different than the theory. And so there's actually a whole collection of different types of tests that people do to compare the signals we get out from these merging black holes with Einstein's theory of general relativity. So far, the theory's held up. General relativity seems to be working just fine. Um, yeah, quantum theory, there are definitely ideas. One of the really neat ideas, and actually there's a few papers out on this. Supposedly, if the dark matter, I don't understand this well, but if the dark matter turns out to be some kind of axions in a particular mass range, then it turns out they'll form clouds around black holes. So you can have these axion clouds around black holes, which would then decay and emit gravitational wave signals, which should be observable. So there are some nice theory papers that describe what these signals should look like. People are looking for that and so far not found it, but they're able to then create upper limits and constrain the mass of the axion particles. So that's cool. And there's a bunch of other ideas. There's lots of other things that people try to kind of poke at both general relativity and different aspects of quantum mechanics. Yeah. Maybe here's one for you, Werner. Do you think you're currently facing any limitations in high performance computing or cyber infrastructure.